Professor Nobuyuki Kaya from Kobe University. This is John Mankins. I am both the first speaker and your moderator this morning. My background is in NASA for 25 years in advanced concept studies and space technology program management. I was formerly the chief technologist for human exploration and development of space at NASA headquarters, and also the lead for NASA for activities concerning space solar power for some years. It's especially appropriate at this 64th IAC Congress that we are discussing space solar power because of the theme of this Congress, which is promoting space development for the benefit of mankind. We have, as I mentioned, a distinguished international panel, including the US, China, Europe, Japan. But I would like to begin for just a moment by reviewing the question, what is space solar power? And I thought it was perhaps very nice to use this illustration to offer you the explanation, which is from an issue this summer of Le Parisien, which did a very nice 3-page article on the topic of space solar power. And so this illustrates the concept of the solar power satellite, which is to deploy into space a large platform at an orbit such that the satellite is almost continuously in the sun, to convert at high efficiency the sunlight into electricity, and then from electricity into a coherent electromagnetic transmission, in this case microwaves, which is then sent in a coherent way to a particular location on the Earth. So this is the fundamental technical concept. The reason why this is very appealing is obviously because the platform in space can receive power from the sun almost continuously. And for a single platform in space, power can be transmitted to a wide variety of locations on the Earth. And so this illustration, for example, shows 2 potential deployments, one in space over the equator above the Pacific Ocean off the coast of South America on the left. And from this one location, using the technology of retro-directed microwave power transmission, which Professor Kaya will describe to you later, you can send power within a very large circle on the surface. Not at the same time, but to a wide variety of locations, including most of North America and most of South America. Similarly, for another platform deployed in the near the equator, near the equator in space, over the Indian Ocean, that's center mark, power could be transmitted from that platform one at a time to locations in Africa, almost all of Africa, all of Eastern and Central Europe, all of the Middle East, India, most of Russia, and most of China and Southeast Asia. Altogether, some 3 or 4 satellites could, in principle, deliver power, depending on the need for power, to a particular location, including 90% of humanity. And this is a remark, and they do it 24-hour days, 24 hours per day, and 7 days per week, with some small exceptions at the points in the spring and the fall when the satellite is in eclipse. So this is the vision of space solar power. There have been, and I will not try in just a few minutes to review all of the details, but I'll just give you the introduction. There have been, over the last 45 years, since this concept was invented, a wide variety of activities, both in the US and internationally. And I would like to just summarize briefly some of the international developments of the past 10 years or so. One is very noteworthy for the IAC, and that is the IAF Power Symposium. So each year, for more than the last 20 years, the International Astronautical Federation Power Committee has organized a session, one or more sessions on space solar power at the IAC this year. This is the longest running international gathering on the topic of space solar power. In addition, there are periodic major international conferences on the topic of space solar power, in which organizations like the IAF Power Committee and like the International Astronautical Federation participate. The International Academy of Astronautics participate, including in 2004 a conference, SPS 2004, which was organized in Granada, Spain, and which the European Space Agency, including the group that is under Isabel, who will speak in a few minutes, helped to organize. In 2009, SPS 2009 in Toronto, Canada, and now in preparation, the next major international conference on solar power satellites, which will be in Kobe, Japan, and which Professor Kaya and Kobe University and myself under the International Academy of Astronautics, working with the IAF Power Committee and other organizations such as the National Space Society, are now beginning to organize for next year to be held in April. And the announcement of that meeting will be coming up shortly. There has also been tremendous media attention to the subject of space solar power, especially in the context of the enormous growth in power demand over the past 20 years, and the now almost complete consensus of the risks of anthropogenic, human-caused climate change, and the growing realization looking out over the next 30 or 50 years that we will begin to deplete with the serious consequences fossil fuels. They're not saying they're going to begin to deplete, is not saying they will be gone, but everyone knows what happens when you have a lot of demand and not enough supply. The prices go up. And so there will be a need for several reasons for new energy sources over the coming years. This, I think, is what has driven the media attention, including the article in Le Parisien, which I showed a moment ago. It includes activity in the TV shows. One was a program on the Discovery Channel, which Professor Kaya will be showing some video from in a few minutes, plus ongoing media and public interest, including coverage in Aviation Week and Space Technology. And I'm about the reporter from Aviation Week who is here. National Geographic magazine last fall did a 3-page article on space solar power. Le Parisien, there was lots of coverage on the internet, one on Fox News just 1 week ago today. And so there's tremendous interest because of this need for new energy. There are a series of selected publications I can recommend to you if you are interested in learning more about this subject. A very important one was the 2011 report from the International Academy of Astronautics study, the first international assessment of space solar power. Another is a report that came out last year for NASA on a new architectural concept called SPS Alpha, a solar power satellite by means of arbitrarily large phased array. This is the illustration, which is here. Also, another very important publication to see is the new Japan Basic Space Law, which came out several months ago, in which, in the new version of the plan, the goal of solar power satellites continues to be one of the fundamental goals of the Japanese space program. And forthcoming, a new book, which I'm the author of, which is called The Case for Space Solar Power. And if you are interested in information, there are some posters on the wall which provide you with information. It's forthcoming. It's being published by the Heinlein Foundation. And there have been a wide variety of activities in terms of international cooperation on space solar power, including the study done for the first International Academy of Astronautics Heads of Space Agency Summit on Climate Change and Green Technology, in which the issues of climate change and the potential for space to contribute solutions was addressed. And one of the topics in that discussion of technology was space solar power. Also, the IAA has formed a global space solar power working group year and a half ago, which meets periodically and is trying to promote ongoing international discussion on this topic. And most significantly, in terms of international collaboration, the former president of India, Dr. Abdul Kalam, has taken as his personal mission to promote future energy solutions, because he feels very strongly that these are critical for the future of India and the future of humanity. And these have included discussions here in China with CAST, and also discussions in the US, in particular with the National Space Society and the Kalam National Space Society Initiative to promote an international activity on space solar power. And Mark Hopkins, the Executive Director of the National Space Society, is here with us this morning. So with that as background, what is space solar power? And well, the broad array of both developments in concepts and the literature and international cooperation. I would like to now turn it to the speakers for this morning. Let me say, as a matter of logistics, that we will be doing the talks for approximately 40 minutes total. So when it's time, I will keep the timer. When it's time, I will tell each speaker, hurry up. And our objective is, at the end of the discussion, that we will have still perhaps 15 or 20 minutes for discussion. There are volunteers here on the side. You can see them very kindly holding up pieces of paper. You can write down your questions if you wish, and they will be provided for the question and answer period at the end of the plenary. Or if we have time, we can also do some spoken questions. There are wireless microphones, so if you do have a question and you don't write it down but you want to ask it, please use the wireless microphone so that everyone can hear it, and we won't have to go through a lot of time trying to say, what did you say? So with that, let me introduce our panelists. So as I mentioned, the first panelist will be Dr. Ye? I apologize. A member of the China Academy of Sciences, and his background is in material science, but he has spoken on several occasions in recent years on the need for new energy, including space solar power and other technologies. Then will come Isabelle Duveau-Béchon. She's the head of the Future Preparation and Strategic Studies Office at the European Space Agency. And lastly, Professor Nobuo Kaya, who is currently the executive assistant to the president of Kobe University, and is one of the world leaders in the particular area of technology of microwave wireless power transmission. So if we could do the switch. And at the end, if we have any time left, I might say a few more words about different activities in the US, but I'm hopeful that that won't be necessary.
Session Chairman. Ladies and gentlemen, good morning. The topics of my presentation is progress and opportunity on space solar power in China. I am from the Institute of Nuclear and New Energy System Materials of University of Science and Technology of Beijing. The former name is the Beijing Institute of Iron and Steel Technology. The outline of my presentation is necessity and opportunities for SSPS in China. And the second is the history of SSPS in China. The third is progress of SSPS in China. And the last one but not least is the roadmaps for SSPS in China. At first, I would like to say the necessity and opportunity for China to develop the SSPS. The energy programs of China is much more serious than in other countries, because the consumption per capita in China is only half of the world, and in comparison with the developed countries, it's about tenth of the consumption per capita, and only 1/13 of the Americans per capita consumption. So we are more now. The CO2 exhaust amount is about occupy 10% of the world, only after the United States. So here is the diagram for the per capita energy consumption in China. It's relatively low, as you can see here. Is China, yeah. It's very low. After the United States, even South Korea, Russia, Japan, and Europe. Here is the UN was the largest user of energy in 2000. But China is now the global leader in energy use. As you can see here, is the global leader in energy use. China's energy demand is expected to continue on upward trajectory projection by the EIA. You can see very quickly increase according to the year. And as you know, now the enhancing space activity of China also urgently need a large-scale spare energy base. So a safe, green, and sustainable energy is the unique selection for China. So it is recognized there are two kinds of energy might be the final solution of the energy crisis in the world. Here is the different renewable and new energy, and solar energy, wind energy, biomass energy, nuclear energy, and other tidal and power. But the ultimate energy and the final solution of energy, people recognize is only these two: is the solar energy or the nuclear energy, especially the fusion energy. But in comparison of these two kinds of final solution, I think that the solar energy is much more easily to be realized than the nuclear fusion energy. Next, I will say something about the SAPS in China, the history of development. From 1997, the Chinese academician Liu Zhenxing has first proposed to follow the international space energy development tendency. And he proposed to develop the fundamental physical process research. In 1995, also a Chinese academician Xu Jianzhong and Yu Mengren and so on, and also give the proposal for as quickly as possible to develop the space solar power station. And also in the Shanghai Space Electric Source Institute, Professor Li Guoxin has several times described the necessity of development of SSPS in China. From the beginning of this century, I have proposed several times to our government and gave the proposal to let the SSPS come to the middle-term and long-term national scientific development program, especially not only the SSPS itself, but also its key materials research is very important. It's one of the bottlenecks for development of the SSPS. And in 2009, October, I was invited to make the academic forum in the space, environment, and material science, make the presentation of SSPS and its key materials, invited lecture in the conference, and gave proposal on the necessity and availability for China to develop SSPS. And in 2010 years, in July 3rd, academician Yu Mengren, Hu Wenrui, Zhang Hongchen, Xing Jiu'en, Cai Ruixian, and me, we 6 academicians gave proposals on development of SSPS and its key materials research to our country, and published in 2010 years the number 3 Chinese Academy academician suggestion. That is published in this journal. Here is for the China, the Space Institute, Space Institute of Space Technology in China has organized several times for SSPS forum, discussed on the SSPS the development linear and related technological problems. And in 2011, led by academician Wang Xiji, he organized and achieved to make the SSPS technology, the development prediction, and the policy report. And with academician Ming Guirong and I and some other totally 6 academicians has given proposals to our country to propose the SSPS as the country's strategy and mass development as soon as possible. Here is in the 2008 to 2012, the 5th Chinese Energy Environment Peak Forum. In this forum, I represent the Chinese academician Wang Xiji, Ming Guirong, Cai Ruixian, Zhou Bingkun, Liang Sili, Rong Ruhao, Yu Mengren, Hu Wenrui, Zhang Hongchen, and the Chinese Academy of Engineering academician Long Luhao, and also the Vice Director of Space Technology Institute of China, Li Ming, to give congratulations and make speech on this peak forum. Here is the SFGS development base and progress. The key technology for the SPS development, first of all, is the photoelectric or thermoelectric energy conversion with low cost, high efficiency, and strong resistance to radiation. The second program must be solved is the transportation between ground and space with low cost. The third is the wireless power transmission by microwave or by laser. And the fourth is the auxiliary semi-autonomous assembly of space robot. And the fifth is the power management and the distribution. Sixth is the highly modular and batch production of structure and components. Seventh is the structure and components with lightweight and long life. And the eighth is electric propulsion with high specific impulse and long life. And then last but not least is the energy storage in space and on ground. And then the basic problem, or one of the bottlenecks, is the material science and technology. And the key problems of SPGS materials is materials for laser transmission systems and materials for microwave transmission systems. And we put the microwave transmission system at the first. Then other key materials for SPS is included laser transparent medium materials. And for my university, we have give two proposals and make research in these two directions. One is with the laser transparent glass ceramics to make the medium. The second is to use the functional graded materials to make the transparent ceramics. And some universities and institutes are working on this area. And in 2012, July, Shanghai Institute of Silicates, or Institute of Ceramics, has successfully studied research on the diameter 150 millimeter high quality neodymium and yak laser ceramics discs. Its photo optical scattering loss only 0.004 cm to -1, and can be compatible with the single crystal materials, neodymium yak. And the Institute of Physical Chemistry of Chinese Academy take LD model, what's it pump to make the neodymium yak ceramics and so on. Here is we use this idea to use the photovoltaic to make transform the main part of the sun energy with the photovoltaic as the visible light, and with the thermoelectric device to transform the other part, the infrared red and infrared violet part energy to the electricity with the thermoelectric device. Here is this diagram for both the photovoltaic cell and the solar electric used to cover almost all the range of the spectrum of sun energy. And China has quite a good base for develop SFPS. Since the 1970s, we began the East Ray first. That is the first satellite we began, and afterwards about hundreds of satellites has been launched, and among them 10 Chenzhou space ship and 2 Moon Explorer satellite, and has been and also the Deep Space Explorer satellite has been. So we at the last I will say something about the 3 stages of development of China SSPS. First is from 2011 to 2020. It's on mainly is on the design and the K technology research. Second is 2021 to 2025 is in the low orbit with 100 kilowatt demonstration. And from 2026 to 2040, about in 2030, we will launch a 10 megawatt demonstration system. So the first commercial space solar power foundation, the scale will be according to the commercial demand.
Our activities will have mainly 3 phases. One that started a bit more than 10 years ago. We'll explain it a bit in the next slides, which is based on, in order to have a view as good as possible of the comparison between space and ground solar power, to make an analysis and independent comparison of the 2 concepts based on the same technology readiness levels, same assumptions for energy needs in 2025, and with the involvement of the terrestrial energy sector, which we think is something important. This is not just for space experts, but of course for energy experts. So I will detail that. Second part is some activities linked to technology maturation or other studies linked to that have been performed, in particular in international cooperation. And the third part is some work that is kind of precursor work before arriving to real space solar power on space and energy at large. So concerning the validation phase, we had a competitive study, so around 2002, giving to the 2 companies that were selected a first concept that they could use as input of space solar power that was based on a sail tower. They were not obliged to use it, but it was at least to give them an idea what could be used. I will not detail the characteristics because the presentation should be in the proceedings, so you will be able to download it. So they were free to use that concept. From that, each of the 2 companies has selected a terrestrial concept to be compared with. One was linked to based on collectors and concentrated power, and the use of for storage of energy, the use of hydro storage. So they were proposing to place the plant in Egypt, east of Egypt, and a place where the desert is not of sand and near to the water, so that they can use hydropower. And the second company decided to base the ground system on the tower option, with storage linked to compressed hydrogen. So each one compared this concept to what they proposed to use as the space solar power. One of them has decided to use the solar tower concept up to 500 megawatt electric level, and the solar disk concept for up power with transmission via microwave to the Earth. And the second study decided to use a laser system transmitting via infrared laser the energy on Earth with this type of concept. By comparing each one, the ground and space solar power, they arrived to a certain number of conclusions that were quite homogeneous. First is that the payback time in energy payback time, not in money, but in energy equivalent, was less than 1.5 years in both systems, with a slightly faster payback for the space solar power. It doesn't mean it's affordable and it's not expensive, it's just energy matters. It is technically feasible, or it will be technically feasible. And of course, they give a certain number of other assumptions, other results. First, that of course, the higher the power level is, the more competitive it is. For example, for the space solar power, the size of the antenna to transmit to Earth will be large, whatever is the power to be transmitted. So the larger, the higher the power you transmit, the lower the cost is per megawatt because of the size of the antenna, just to give an example, and there are other considerations like that. What was considered as an open parameter is the launch cost, taking some boundary margin. We didn't want them to make assumptions on launch costs that might be unreasonable, so it is one of the parameters that will have to be taken into consideration. So the cost that were considered was in this order of 500 to 1,000 euro per kilogram. And there was still, of course, a need of a lot of analysis for the integration of this power from space into the ground system. There were a certain number of experiments that followed or that were done in parallel. One of them, I'm sure, will be mentioned by Kaya-san, which is the Furoshiki experiment that was done in collaboration with the University of Kobe in particular, for deployment of a net and wireless power transmission. Just an example here, the European part was with robotic movement, some robots that were moving on a net. It was tested on a parabolic flight. So the robot is just moving on the net, which would be used to assemble the net. This was launched on a Japanese sounding rocket in 2006. And it showed that the result was successful, the experiment was successful. The concept was possible, but a bit possibly complex. So as a first step. And then later, we defined another experiment, at this time flown on a European Rexus sounding rocket, working with universities of Glasgow and Stockholm, and on the concept of centrifugal deployment of net. With here you can see how it looks like. So by centrifugal forces, the net was being deployed. This was launched in 2012, so for a small element. Some data were recovered directly during the flight, but most of the data was stored on board. And the return capsule has got some problems at landing and was just recovered a few weeks ago. So 1 year after the experiment. So they will be analyzed, and we hope that it's not too damaged by the return that was a bit less than optimal. So we'll see if we get some more results, but it won't. There were two small preparatory studies that were performed, one already 10 years ago, which was to study the legal aspects of the solar power satellites and what were the impact of all legal provision that would have to be applied once this would have to be developed. So this gives a basis for the future analysis on that. And the other one was an internal research study that was done in the advanced concepts team on assembly of solar power, autonomous assembly of solar power, having some modules that would by themselves unite them into a configuration that had been predefined, but without the hand of a controller, so that to see how it could lower the cost, ease the integration by releasing the swarm in low Earth orbit and having them spiraling to the final geo orbit and assembling themselves into a given shape. The third part I mentioned is linked to the space and energy. What we thought is that This solar power system, it will be feasible, it will be done. I mean, you've got already elements from the former speakers. It's a bit immature for the moment for real implementation at large scale. So we think that what's important is first to embark the energy sector, because in any case they will have to be involved. So the earlier they learn to work with the space sector, the earlier we can combine the forces, combine the technologies and the development, the better it will be for the next step that will involve space solar power. So we have an initiative called Space for Earth, in which we make links between sectors that traditionally are not linked. It doesn't mean that energy sector doesn't use space data, but they use space data as any other data. They are not used to work with the experts. And we define with them technologies, applications, what are their future needs. And it's involved, in fact, all these other domains. I mean, all activities, not only the studies. The objectives are, of course, to go on with development of applications. I mean, this is still valid. And we have two new components that are being developed, one on technologies with synergy between ground and space sector, and one on what would be the need for infrastructure in the future, with three examples of answers to be given. One, to support energy-related regulation, for example, thermal efficiency or buildings. One on supporting the renewable energy in general. And one to complement the terrestrial very large space power infrastructure. So this part would fit into the space solar power and preparation of all that. Just to conclude, so we have performed this initial analysis, at least to be able to know how we can compare what can be done in space, what can be done on the ground, to see where is the interest and to confirm the interest of space solar power. The concept is not yet mature, but still it will be in the next years. It is suitable for international cooperation. It already started and it has to be continued, and innovative approaches, clearly. It will require technology maturation, which is one of the elements that can be worked already today. And this wider initiative will help to have the space sector and the ground sector understand each other and work together. And most of what we are doing, in fact, is done in the frame of the advanced concept team of ESA, and you have the head of the team here, Leopold Summerer, that can give you a lot of more information if you need after that. And we hope that we can continue, especially in collaboration on that.
Hi, I'm from Kobe University. So I would like to talk about our technical development, mainly developed on microwave power transmission. So this chart shows a very famous SPS concept developed by NASA and the DOE in 1979. So you can see this system has a very big solar cell, 5 kilometers by 10 kilometers. And so solar cell connected to the microwave transmitter, this part. So solar cell must face to the sun always. So, but the microwave transmitter must face to the ground. So we need a big rotary joint between the solar cell and the microwave transmitter. So it is a big issue, and it looks very difficult to realize. So this is our concept of the solar power satellite. This system is very simple. This system has only reflector and sandwich structure. Sandwich structure consists of solar cell on the one side, and on the opposite side we install a microwave power transmitter. So solar cells are connected directly to the microwave transmitter. So this realizes many modules. So and it is very easy to construct just on touch attached to the with the main module. So, but this so in order to realize the solar power satellite, so we have to reduce the weight. So because launching cost must be reduced. So then transmitting antenna sandwich module must be very light, very thin. So it maybe so structure is very flexible. So and antenna transmitting antenna is moving and oscillating bigger distortion. So but we have to control the microwave beam to the ground station. So always we have to keep the microwave beam accurately to the ground station. So we need some breakthrough. So we developed the electrodirective system. So this system is very simple. So on the ground, we have a big transmitter to radiate pulse signal to the solar power satellite. So each antenna element receives the pulse signal to measure the phase of the pulse signal. So it is easy to control the output phase of the high power microwave from the space antenna to the ground to the external. So this is the main theme for my development. So, and fortunately, we have many opportunities to perform the space experiment and demonstration. So, 1983, or just 30 years ago, so very long time ago. And this is the first sounding rocket experiment. So, and the second is 1993, 10 years later. So we test for the investment to the influence of the high power microwave to the space environment, especially plasma. So and we nonlinear interaction between high power microwave and the plasma is expected. So this is our result. Horizontal axis is frequency and amplitude. Vertical axis is shown the amplitude. So this line is natural waves. So but when we turn on the microwave, high power microwave, so and these portions are excited. So it is a very interesting phenomenon in physics. So but this is not this is electric static waves. So are not propagated. So are not influenced to the radio and telecommunication. So anyway, so I want to explain our recent space experiment. We launched so many times. I'm sorry. 2006, we launched sounding rocket. So Isabella mentioned about our sounding rocket experiment. So we assembly how to construct the solar power satellite is another issue. So solar power satellite is very huge. So and diameter is 1 kilometer, over 1 kilometer, and the reflector is over 5 kilometers. So very huge. So and it is a very big problem issue to how to construct. So but our idea is deploy large mesh, so to make a mainframe. So we try to deploy the large mesh using sound rocket. And this is a parabol antenna. We ready transmit pulse signal from the large antenna from the ground to the payload. Payload has 4 antenna elements to work as a retrodirect antenna system. So this is the result. So horizontal axis is the time, and the vertical is the receiving power. So if our system is work very well, so and receiving power must be constant. So this chart shows the turn of the retrodirect system. So you can see the receiving power is very changing. So, but when we turn on this portion, this part, almost constant. So it shows our system is very, working very well. So anyway, this is the first trial power transmission over 100 kilometers. So power from space to the ground. I think this is the first experiment. So and the next is John mentioned about the Discovery Channel. So we have a very good opportunity to taking us our experiment demonstration by Discovery Channel. Discovery Channel is a very famous science channel. So this is a transmitting antenna developed by our student. And the receiving antenna. Anyway, in Hawaii, we have a tall mountain volcano in Maui Island and Hawaii Island. So we try to power transmission from Maui Island to the Mauna Loa. So the distance is over 150 kilometers. So just like so from space, between the space to the ground. So you can see Mauna Kea and the Mauna Loa high mountain. So if this is a program. So but I have no time. So and I'm sorry. Maybe you can find this film program. So and please watch this program. And next is a very important experiment. Rich guy watched our TV show. So and he suggested me to support our demonstration. So he held an international conference in Toronto in 2009. So I gave him a promise to perform the demonstration on the microwave power transmission. So we developed the active phasor array antenna with a retrodirect system. So anyway, this picture shows our demonstration. This is a transmitting antenna, and this is a receiving antenna. Yeah. Anyway, our system, in our retrodirect system, this is a transmitter of the power signal. So anytime some microwave radiated from the transmitting antenna concentrate to the power signal antenna. Okay, so power signal, anyway, microwave is concentrated here. So this is just an antenna. and just connect the antenna connected to the LED lamp. You can see a LED lamp is bright. Can you see? So it means microwave is concentrated here, focused here. Okay, just you can see a bright LED lamp. So if away left give from the transmitting antenna, so microwave will not reach to the receiving antenna. So, but the microwave is a power signal transmitter. So our system is control the microwave beam according to the position of the power signal. Okay, turn off. Okay, this is the final. So please, now bright. Same experiment. So, but bright, keep bright. Okay, this is a antenna to connect to the motor. So if so receive microwave power and moving and approach and turn on and it can move. Okay, can you understand? Okay, that's my technology. So, but I think next step must be a satellite experiment to verify our electronic system. So, I hope I will have a good chance. Thank you very much for your attention.
Submit proposal of our government, and response is very good. And project has been approved later by the Institute of Space Technology. I am the advisor. So we are now government have more support to make a large project.
So another question.
Frequency is a 2.45 gigahertz. So it is a wavelength is a 10 centimeter. So it long for the effect to the weather, or we have no alternation in day and weather. So I believe it is no difference to the weather.
So the case of the sail tower concept that you showed in your movie, why is it so long?
Well, the length is just a function of the power you want to transmit. So in fact, it can have any length. Depending on short, it will not have economic value to be built because of what I mentioned of some antenna so that have to have a special size. So the length will be adjusted to whatever is needed, but in any case, it will be long. Space solar power will never be small.
So, and the other question, an associated part of that question was why not make it, instead of long and thin, make it broad and short?
Well, it's the same, I would say.
Same area.
The concept, just one concept, it doesn't mean it will be the one that will be selected. Others have been studied. It was just to give an idea to the energy company, or energy consultant that were in charge of the study, so that they have a point of departure. But of course, it could be different.
So I will take and I apologize for that. And this was a question concerning the transmission of power from the solar power satellite, and the question of how to assure that there's no conflict with the International Space Station and with the Chinese Space Station or other infrastructure in low Earth orbit or lower orbits from the solar power stations. And so the question is a very good one, and of course has to be looked at, and I think that in general there are really a couple of answers. One is that for assets that are in GEO, the intensity of the power transmission solid state amplifiers in a very, very, very narrow bandwidth. So almost exactly, for example, 2.45000 gigahertz. So it's a very tiny part of the electromagnetic spectrum. So over time, not necessarily tomorrow, but 10 years or 20 years from now, future spacecraft could have the notch filters that would protect the electronics from those parts of the spectrum that involve the power transmission. And lastly, of course, because the time is extremely short, the object in low Earth orbit is moving at approximately 5 or 6 or 7 kilometers per second, 7 kilometers per second, and the width of the beam is only on the order of 10 kilometers at most. The time of transit is quite brief. It's on the order of 1 second. And so it certainly may be possible to beam back on. And this should be easily engineered at the ground system. So it should be perfectly possible to one, have low risk even if everything fails, two, to have filters to protect, and three, to turn it off in the case of key systems like space station with people. And I think with that, we really are way over time, and I appreciate the volunteers for allowing us to go a little long, because they have other things they must do. And I would like to just say thank you one more time to the audience at this plenary and to all of the participants in the panel for this very interesting and exciting discussion. So thank you.